Welcome to our 8th lesson on electrochemical reactions. We'll be taking another look at some questions that you can expect in a test or exam. Now the question starts off by telling us the cell notation of a standard galvanic cell containing an unknown metal, which is seen as electrode X, is then shown. Now due to spatial restrictions, we won't be able to have it all in one line. So we start off with this electrode X in the solid form, and we'll see that it ends up forming 3+ ions, which is obviously the aqueous form, together with the electrolyte concentration at standard conditions. We have our salt bridge, followed by what's going to happen in my cathode, which is the lead ions, that's going to form lead solid. Now the first question asks us to go and name the components of the cell that's represented by those double vertical lines. Now the double vertical lines refers to our double lines over here, which indicates the salt bridge. So the first answer is thus salt bridge. Now the next question is slightly different to what we used to have it. It asks us to state the two standard conditions that will be applicable to only my lead half cell. Now our lead half cell has Pb2+, and that means that it is in the aqueous phase, and we're going to have lead, and all by itself it's in the solid phase. So once again, here we will not have any specific pressures because we don't have any gases. So the two standard conditions would be temperature of 298 Kelvin or 25 degrees Celsius and an electrolyte concentration of 1 mole per cubic decimeter. Our question number 3 asks us to go and identify the oxidizing agent in the above cell. Now remember, oxidizing agent means that we're talking about the cell that's going to go reduction. And reduction is the part that occurs at the cathode. Now our cathode part is always written after the salt bridge, and that's going to be our Pb2+ going to Pb. But to identify the oxidizing agent, it's always the very first part that our reduction half reaction would start with. So it starts with Pb2+ going to Pb, so that's how come Pb2+ is going to be, in this case, the oxidizing agent. Do take note that it's not Pb, it must be the ion of Pb, that is Pb2+. Now question number 4 is also a question that's slightly different to what we used to up till now. It asks us that the initial reading on our voltmeter connected across the electrodes of the above cell is 1,53 volts. Go and identify the metal X by calculating the standard reduction potential of this unknown metal X, and then obviously we'll need to take that value and compare to the values on the redox table to see which one of those would then be close to this metal X's value. So the values though given up till this point is that of the total E cell, and that is our 1,53 volts, and we do know that the other cell, which is the cathode, which undergoes reduction, is my lead cell. So we need to go and take a look at what will be my reduction E cell value for my lead. Now lead's reduction E cell potential value is negative 0,13, so that's then our value that we'll be using for my reduction E cell value. Let's now go and add them back into our equation. Now you can pick any of the formulas that is given on the formula sheet. I'm just going to use the reduction minus oxidation one. Note the E cell is given as 1,53. The reduction we've read off the table to be negative 0,13 for lead, minus my E of oxidation, which I do not know, and this is my electrode X, which we would like to go and calculate. Now our E cell oxidation value ends up being a negative 1,66 volts. Now if it's a negative, you need to leave it as such, and we need to go and look on my redox table for a negative 1,66 value. Now once looking for the negative 1,66 value, we're going to find that that is exactly the value for my aluminium. That means that my aluminium is going to be my oxidation half reaction that occurs at the anode. And X is thus identified as aluminium. The next question asks us to write now a balanced equation for the net overall reaction taking place in the cell, leaving out the spectator ions. So omit means leaving out. And our spectator ions would then be everything that is not included in the oxidation and reduction half reaction. Now, although they ask only for the overall reaction, you'll have to, for yourself, do the oxidation and reduction half reactions. Now, just due to limited space, I'm going to abbreviate my oxidation and reduction half reactions as such. We know that oxidation is the one that's aluminium, and that's now going to start with aluminium, ending up being aluminium 3 plus 3 electrons as I'm reading it off from right to left on my redox table. The other one is lead. Lead though starts off on the left hand side because it's going to be my reduction half reaction of Pb2 plus, gaining 2 electrons and then ending up forming Pb solid. Now once again, what's unique about all of my redox reactions or my overall reactions is that my electrons must completely cancel each other out, and they must do so by doing a cross cancel from the left and the right hand side. In this case, my oxidation half reaction has got 3 electrons and my reduction has got 2. So I'm going to need to go and find a common denominator which both of them can divide into, and that's going to be 6. But in order to get my 3 electrons to 6, we're going to multiply by 2, but everything will then end up being multiplied by 2. So 2 aluminium ions, and that 2 times 3 then becomes 6 electrons. If I take a look at my lead half reaction, note that it's got a 2, so to get 2 to 6, we're going to multiply everything by 3. And we'll see that my electrons now are both 6 and can thus cross cancel from the left and the right side out. Now there's nothing else that looks the same, so that means my overall reaction would thus be 2 aluminiums in the solid phase. Now we're going to add up everything, remember, on the left hand side and the right hand side of the arrows, plus 3 lead ions, that's going to be in the aqueous phase, and they're going to end up forming 2 aluminium ions in the aqueous phase, plus 3 lead atoms in the solid phase. So the final answer is thus only this overall reaction, not these 2 oxidation reduction half reactions, but you'll need to do them for yourself in order to go and see what will be this overall balanced net reaction. Now the moment that you are multiplying by 2 and 3's here, you are already balancing the equation. So if there was though no need for you to add in the 2's or the 3's, then it would have been balanced the moment that you add up and completely cancel out the electrons. Now the next question asks us, how will the initial voltmeter reading be affected if the concentration of the electrolyte in our X solid going to the X3 plus aqueous half cell is going to be increased? So note though that it's the electrolyte that is going to be increased, and that means it's the ionic form X3 plus. Now here's my overall reaction. We now know that this X3 plus is actually my aluminium 3 plus. So they would like to know what's going to happen to the EMF if this electrolyte concentration is increased. Now remember, according to Le Chatelier, it would like to oppose the change by decreasing this electrolyte solution, and it will do so by favoring the reverse reaction, which means that my EMF, which is the voltmeter reading, will end up decreasing whenever the reverse reaction is favored. Now the last question asks us to write down the value of the reading on the voltmeter when the cell reaction has reached equilibrium. Now when the cell reaction has reached equilibrium, we would see this as the cell has become flat, and that means that our voltmeter reading on it will be 0 volts.